Hey, it's Ken the Metal Professor. I am jumping in here with just a quick sample problem that was spurred by a question on Reddit yesterday or the day before, because it reminded me of a little trick that I used to teach my students when they were solving problems involving solids of revolution, right? Take a curve, spin it around an axis, find the resulting volume. And those problems are pretty straightforward when the axis of revolution that you're spinning around is either the x-axis or the y-axis, but the problems get a little bit more difficult, especially your first time through, when you take something like, let's take y equals sine of x from 0 to pi, right, and revolve it around y equals -1. All right, and so that's a slightly different story, and that can be a little bit tricky to set up your first time through. So here is a suggestion of how to deal with that, if I can get to my screen here to advance a slide. All right, so the basic problem is you have a function, let's say between x equals a and x equals b. You're going to spin it around the x-axis. In that case, the cross sections are circles or disks, and so you use the disk method or the washer method if there's two functions to calculate the volume, right? You just collect up a whole bunch of pi r squareds, in other words, pi f of x squareds from one side to the other through an integral, and that's how you get the resulting volume. If you take that function between the same two x endpoints, but this time swing it around the y-axis, then my finger is like one piece underneath that function. I swing it around like that. I've made a cylinder. The area of a cylinder is 2 pi rh, and so we go out to the point, that's the x coordinate or the radius of the cylinder. The height of the cylinder is f of x, and so when you're swinging around the y-axis, you are making cylinders from every contributing sliver under the function, and so you collect all those areas to create an overall volume of 2 pi rh, or 2 pi x f of x. So these are the two straightforward volume formulas for those scenarios, and the integration usually ends up pretty simple. The problems are engineered to not be too difficult, but like I said, they get a little bit more interesting when the axis of revolution isn't one of the axes, but is some horizontal or vertical line that's offset. And your options are to go back and think about your Riemann sums, and, well, how can I adjust what I'm thinking about if I'm making a cylinder, what I'm calling R or H, how does that change? Or for disks, how does the radius of the cross-sectional circle that I'm making with the revolution change because of the new axis of revolution? And I think that's where people get a little bit more slowed down in that process. Now, the other option is just to change the problem to one that's a little bit better. So here's what we're going to do. If you're given an axis of revolution that isn't one of the axes themselves, instead of going back and trying to redesign the process from scratch and coming up with a modified volume formula, you're just going to take that curve and the axis of revolution, you're just going to pick the whole thing up and set it down again so that you are now revolving around one of the axes. Because if I take this curve and I'm revolving around this axis and I lift it up, and now here's, say, the x-axis that I'm revolving, it's going to be the same volume. It's just going to be a translated function. So the key here is not necessarily redesigning the Riemann sum business, but just translating the problem to solve an equivalent but easier problem. Now, I know the point is to practice with thinking about Riemann sums and how the integration process works, but you don't always have an infinite amount of time. Oh my gosh. If you've seen my videos before, every time I start making a video, the dogs start barking from something outside. So I'm going to pause for a sec. Okay, they stopped, but now that I'm talking, they're going to start again. So this is the actual question that inspired me to make a quick video about this. Find the volume that results when the region between y equals x squared, x equals 1, and the x-axis is revolved around the line x equals -2. So normally this would be a cylinders problem because we're taking y equals x squared, we're clipping off a little piece of it, and then we're swinging that around the y-axis. So every sliver under the curve during this revolution process is sweeping out a cylinder, and we would collect up all the weighted areas of those cylinders. to generate the overall volume through an integration. Okay, but the revolution is not happening around the y-axis itself. It's happening around the line x equals -2. So that's 2 units away from the y-axis. So again, option 1 would be think through the partitioning process, the Riemann sum business, reconstruct a brand new volume formula involving integration, or just pick up y equals x squared and x equals 1 and pick it up and move to the left by 2 units, plop it down again. That new curve revolved around the y-axis will give you the exact same volume as this one. Okay, so we are going to give that a try. We're just going to pick it up, move it to the right, and plop everything back down. So let's take those ingredients one at a time. You have to remember how to translate functions, but that's not too bad if you're in Calc 2. Shift to the right by 2 units. Y equals x squared. Moved to the left by 2 units becomes y equals x minus 2 squared. The boundary at x equals 1 becomes x equals 3. And x equals -2, this is the point of the problem, shifted to the right becomes the y-axis. Here's a picture, badly drawn, but the top figure is the original problem. X equals -2 is the axis of revolution. You got your parabola y equals x squared, you got x equals 1, you got the x-axis. So you're doing that revolution around x equals -2. We say thanks but no thanks. We just pick up the entire problem, move it over, plop it down, move it over 2 units, and now we have the function y equals x minus 2 squared, trapped at x equals 3, right? That's the farthest away we go. That being revolved around the y-axis is going to give exactly the same volume. Okay, so there's the new problem. Y equals x minus 2 squared. X equals 3 and the x-axis being the boundaries, revolving that around the y-axis, and now we can just build that integral formula straight up using the regular old solid of revolution volume formula through integration. 2 by x, f of x. Just now the function is x minus 2 squared, and we're integrating from 0 to 3. Okay, again, there's the picture, right? The red shading is the region that's being revolved around the y-axis from 0 to 3. Underneath, y equals x minus 2 squared, out to 2, x equals 3. And I don't even have the value for this integral because it's so straightforward. You could do it if you needed to. Okay, and then just as a second example, make this a little bit quicker. Let's say we have the square root of x plus 1. So the square root function, we're going to move, that's already raised up by 1 unit. We are going to draw the line y equals 1 underneath it, and then boundaries at x equals 1 and x equals 4, and we're going to revolve that around y equals -3. Now that sounds gruesome because the axis of revolution is not one of the axes, it's y equals -3, so 3 units below the x-axis. So the square root curve is up here, y equals -3, doing that revolution, okay? Yuck. Either go back and reconsider the partitioning and the Riemann sums and things like that to build up to a new formula, or say thanks but no thanks. I'm going to find the equivalent volume. I'm just going to take everything in this problem, I'm going to lift it, pick it up by 3 units and plop it back down and solve that new problem. And that would get us the equivalent volume. So if we take y equals root x plus 1, shift that up by 3 units, that's now y equals root x plus 4. The axis, the bounding below axis, y equals 1, becomes y equals 4. The left-hand endpoints remain the same, right? The vertical shift doesn't have anything to do with x equals 1 to x equals 4. And the key to this is that the axis of revolution that was y equals -3 becomes the x-axis. So this is a disks problem, or actually it's a washers problem, because we have y equals 1 as the lower edge underneath the square root curve. So that, what is that shaped like? I don't know. It's not really a banana. Whatever it's shaped like, that region is getting revolved around what used to be y equals -3 and now is the x-axis when we move it up. So here's the new problem. Find the problem, or the volume that results when the region between y equals root x plus 4, y equals 3, x equals 1, and x equals 4 is revolved around the x-axis. That one, we can just plonk those things right into the standard volumes by disks type of formula. Pi r squared for the outside, that's the root x function. Pi r squared, that's just the volume found by revolving the lower boundary y equals 3 around the x-axis between x equals 1 and x equals 4. Boom, you're done. Solve that integral and you've got it. Okay, so this is just a little bitty hint for problems like this. I hope it helped. Make sure you draw yourself a picture of this problem to make sure you see what's going on, because I did not draw that picture, obviously. And yeah, that's all. Thanks for watching. Hope it helped.